There's a spacecraft right now flying through the dark, more than 15 billion miles from where you're sitting. It's older than most of the people watching this video. It was built with less computing power than the phone in your pocket. And it just did something no human-made object has ever done before. It left, not left Earth. We've done that thousands of times. Not left the moon or Mars, or even the orbit of Pluto. This thing left the solar system entirely. It crossed an invisible wall in space that scientists had theorized about for decades, but had never ever touched. And when it crossed that wall, it started sending back data that made researchers stop in their tracks. Because what's out there, in the space between the stars, was not what anyone predicted. For 60 years, we thought we knew where our solar system ended. We thought we knew what the edge looked like, what it was made of, how the sun's reach faded into the cold dark of the galaxy. We were wrong about almost all of it. And the thing is, the edge of the solar system isn't where you think it is. It's not Pluto. It's not Neptune. It's not even the last little chunk of ice drifting in the outer dark. The real edge, the true boundary, where our sun's empire ends and the rest of the Milky Way begins, is something far stranger. It's a wall made of magnetism and superheated plasma. It's a shield that's been protecting your body and every living thing on Earth for billions of years without you ever knowing it was there. And until 12 years ago, no one had ever seen it from the inside. This is the story of how two tiny spacecraft, launched back in 1977, outlived their mission by half a century and became humanity's first explorers of interstellar space. It's the story of what they found when they crossed the edge. And it's the story of why that discovery is forcing scientists to completely rethink our place in the galaxy. So stick with me, because by the end of this, you're going to understand something almost nobody does. You're going to know what's actually out there, beyond the edge of everything we call home. Let's get into it. Let's go back to the beginning to understand what just happened out there. At the edge of the solar system, you have to understand the two machines that made it possible. And honestly, the story of how they even got there is half the miracle. It's 1977. Jimmy Carter's in the White House. Star Wars is in theaters. A gallon of gas costs about 65 cents. And at NASA, a team of engineers is preparing to launch two of the most ambitious spacecraft ever built. They're called Voyager 1 and Voyager 2. And the mission, on paper, was actually pretty modest compared to what they'd eventually become. The plan was to send them on a grand tour of the outer planets, Jupiter, Saturn, and if everything went perfectly, Uranus and Neptune too. See, there was a once-in-a-lifetime opportunity hiding in the math. The outer planets were lining up in a way that only happens roughly once every 175 years. If you launched at exactly the right moment, a single spacecraft could use the gravity of one planet to slingshot toward the next, and the next, and the next. It's a technique called gravity assist, and it meant Voyager could visit 4 planets using almost no fuel, just borrowing energy from the planets themselves as it flew past. Missed that launch window. and you'd be waiting almost 2 centuries for the next chance. So they took it. Voyager 2 actually launched first. On August 20th, 1977. Voyager 1 followed about 2 weeks later on September 5th. And here's a little detail that trips people up. Voyager 1 launched second, but was put on a faster path, so it overtook its twin and pulled ahead. That's why it's Voyager 1. It's the one out in front, and it's the one that would eventually become the most distant human-made object in existence. Now I want you to really sit with what these machines were working with, because it's almost comical by today's standards. Each Voyager carries a computer with about 70 kilobytes of memory. Total. Your average smartphone has hundreds of millions of times more. The cameras, the sensors, the whole spacecraft, all of it runs on less power than a typical refrigerator. And they don't run on batteries or solar panels, because out past Jupiter, sunlight is far too weak to be useful. Instead, each Voyager carries a chunk of plutonium that generates electricity through radioactive decay, slowly, steadily, for decades. That tiny trickle of power is the only thing keeping these spacecraft alive, and it's been fading a little more every single year since 1977. And yet, these primitive little machines went on to do extraordinary things. As they swept past the giant planets, they sent back images that rewrote the textbooks. They showed us active volcanoes erupting on Jupiter's moon Io, the first time we'd ever seen volcanic activity anywhere besides Earth. They revealed the stunning detail of Saturn's rings, thousands of individual ringlets braided together by gravity. Voyager 2 became the only spacecraft in history to visit Uranus and Neptune up close, and to this day, it's still the only one. Everything we know from seeing those two ice giants with our own eyes, we owe to a single spacecraft from the 1970s. But here's the thing. The planetary tour, as incredible as it was supposed to be the end of the story. Once Voyager 2 swung past Neptune in 1989, the headline mission was technically over. The cameras had done their job. The planets were behind them. By all rights, that should have been the finale. It wasn't, because the engineers realized something. These spacecraft were still working. They were still powered. They were still pointed outward, falling away from the sun at tens of thousands of miles per hour, with nothing ahead of them but the vast, empty dark. And out there, in that dark, was a question nobody had ever been able to answer directly. Where does the solar system actually end? So NASA did something clever. They kept the mission alive. They shut down the cameras since there was nothing left to photograph, and they redirected all that precious power toward a different set of instruments. The ones that measure particles, magnetic fields, plasma, the invisible stuff. Because the next chapter of the Voyager mission wasn't going to be about seeing things. It was going to be about feeling the boundary of the solar system from the inside as the spacecraft pushed through it. And that meant the two oldest working spacecraft in human history were about to become something nobody had planned for when they were built. They were about to become interstellar explorers. So, the spacecraft are heading outward into territory no machine had ever explored. But before we follow them across the edge, we need to talk about what that edge actually is. Because this is where almost everyone's mental picture of the solar system turns out to be wrong. Ask most people where the solar system ends, and they'll say Pluto. Makes sense, right? Pluto was the last planet, the final stop on the lineup we all memorized in school. After Pluto, you'd think there's just nothing. Empty space all the way to the next star. But that's not how it works at all. Pluto isn't the edge. Pluto is barely out the front door. Here's the truth. Our sun isn't just a ball of light sitting quietly in the middle of the solar system. It's blowing. Constantly. Every second of every day, the sun is hurling a storm of charged particles out into space in all directions. This stream of particles is called the solar wind, and it screams outward at speeds of up to 1,000,000 miles per hour. It doesn't just drift. It rushes out past Mercury, past Earth, past Jupiter and Saturn, filling the entire solar system with a thin, fast-moving gas of electrically charged particles. And as that solar wind pushes outward, it carves out a gigantic bubble around the sun and all the planets. Scientists call this bubble the heliosphere. Think of it like this. Imagine you're standing in a heavy downpour and you turn a leaf blower on, pointing it straight up. The air blasting out would push the rain away, carving out a little dry pocket above your head. The sun does the same thing, but on a scale almost impossible to imagine. The solar wind blasts outward in every direction and pushes back against the stuff that fills the space between stars, carving out a vast protected bubble with the entire solar system tucked safely inside it. Now that bubble has to end somewhere, because the solar wind can't push forever. The further it gets from the sun, the weaker it becomes, spreading thinner and thinner across an ever larger volume of space. And eventually, way out there, it runs into something. It runs into the interstellar medium, the actual material that fills the galaxy between the stars. This is gas, dust, particles, and magnetic fields left over from billions of years of stars living and dying across the Milky Way. It's incredibly thin, almost a perfect vacuum by everyday standards, but it's not nothing. And it's pushing back, so picture two forces meeting head-on. From the inside, the solar wind racing outward, trying to expand the sun's bubble. From the outside, the interstellar medium pressing inward, trying to crush it. And at the exact point where these two forces balance, where the sun's outward push finally matches the galaxy's inward squeeze, you get a boundary, a wall. This is the edge of the solar system, the real one, and it has a name, the Heliopause. This is the true border of our sun's territory. On one side of it, everything is controlled by the sun. The particles, the magnetic field, the whole environment, all of it belongs to our star. Cross to the other side, and suddenly you're in the galaxy proper. The particles around you came from other stars from supernova explosions that happened millions of years ago and light years away. The magnetic field belongs to the Milky Way, not the sun. You've left home. And here's a number that'll reset your sense of scale completely. That boundary, the Heliopause, sits about 11 billion miles from the sun. That's roughly 120 times the distance from the Earth to the sun. Pluto, by comparison, averages around 40 times that distance. So the real edge of the solar system is about 3 times further out than Pluto. When you finally cross the Heliopause, you have traveled so far that the sun, the star that gives us all our light and heat and life, is just another bright dot in the blackness. A particularly bright star, sure, but a star lost among thousands of others. Now, for decades, the Heliopause was almost a theoretical thing. Scientists knew it had to exist. The physics demanded it. The sun is blowing a bubble, the galaxy is pushing back. So there has to be a boundary where they meet. But knowing something must exist and actually measuring it are 2 completely different things. Nobody had ever been there. Nobody had ever felt what it was like to pass through that wall. All the models, all the diagrams, all the predictions about how thick the boundary was, how the magnetic fields behaved, what the temperature was, all of it was educated guessing. Sophisticated guessing, but guessing all the same. And this is the part that matters. The scientists had built detailed models of what the crossing should look like. They had expectations. They figured the boundary would be a wide, messy, chaotic region. A gradual blending zone where the sun's particles and the galaxy's particles would slowly mix together over a huge stretch of space, like the muddy water where a river meets the ocean. They expected turbulence. They expected the transition to be sloppy and spread out and gentle. They were about to find out just how wrong those expectations were. Because Voyager 1 was getting close, and when it finally hit that wall, the data it sent back didn't match the predictions, not even a little. For years, the scientists watching over Voyager 1 had been waiting, watching the data trickle in, looking for any sign that the spacecraft was approaching the boundary. And there were teasing hints. Starting around 2004, Voyager began detecting strange changes in the particles around it, signs that the solar wind was slowing down, getting sluggish, starting to pile up the way water bunches up in front of a slowing boat. The spacecraft had entered a region scientists call the Helios sheath, a kind of turbulent outer layer of the bubble where the solar wind, after racing outward for over a decade, finally starts to lose steam and slow to a crawl. For years, Voyager pushed through this region, and the team kept watching, kept waiting for the real moment, the actual crossing of the Heliopause itself. The problem was, nobody knew exactly when it would happen. The boundary doesn't sit at a fixed distance. It breathes. As the sun goes through its activity cycles, getting more and less active over the years, the bubble inflates and contracts. So the team couldn't just circle a date on the calendar. They had to watch the instruments and wait for the signs. And then in 2012, the signs came, and they came suddenly. Here's what happened. Voyager 1 carried instruments designed to count two very different kinds of particles. On one hand, particles coming from the sun, the slow, lower energy stuff, carried out on the solar wind. On the other hand, galactic cosmic rays, which are extremely high energy particles that come screaming in from the rest of the galaxy, produced by violent events like supernova explosions far across the Milky Way. Inside the heliosphere, the sun's bubble blocks a lot of those cosmic rays, so Voyager saw relatively few of them. Outside the bubble, in raw interstellar space, the cosmic rays should come flooding in. So those two numbers, the count of solar particles and the count of galactic cosmic rays, were the key. They were the tell. If Voyager ever truly crossed the Heliopause, the solar particle count should crash, and the cosmic ray count should spike. And in 2012, over a remarkably short period, that's exactly what happened. The drop was dramatic. The number of particles coming from the sun didn't fade away gradually over years like some had expected. It fell off a cliff. In a matter of weeks, the solar particles that Voyager had been swimming through for 35 years nearly vanished. The level dropped by a factor that left no room for doubt. And at almost the same moment, the galactic cosmic rays jumped. The high energy radiation from the wider galaxy surged upward and held steady at a new, much higher level. The two lines crossed. The sun's influence collapsed, and the galaxies took over, and it happened fast. On August 25th, 2012, Voyager 1 became the first human-made object to cross the Heliopause and enter interstellar space. It was, no exaggeration, one of the most significant moments in the history of exploration. For the first time in 4.5 billion years, something built by life on Earth had left the sun's bubble and entered the wider galaxy. And there was a kid from the 1970s flying the flag, an antique spacecraft running on less computing power than a digital watch, doing what no machine had ever done. But here's the wild part, the part that caught everyone off guard. Remember those predictions? The expectation that the boundary would be a wide, gradual, chaotic blending zone? Voyager found the exact opposite. The transition was sharp. It was narrow. It was decisive. One side, the sun. Other side, the galaxy. And the wall between them was far thinner and far more clearly defined than anyone had modeled. It wasn't a muddy estuary where two waters slowly mixed. It was more like a coastline, a genuine edge. You were either in the sun's territory or you were in the galaxy's, and the strip of space separating the two was startlingly thin. That single finding forced scientists to start reworking their models almost immediately. If the boundary was that sharp, then something was holding it together. Some physics they hadn't fully accounted for was keeping that wall crisp and distinct instead of letting it smear out the way the equations had suggested it would. And that was just the first surprise. Because as Voyager kept transmitting from the far side of the boundary, the data kept getting stranger. So Voyager 1 is through. It's on the other side, in true interstellar space. sending data back across 11 billion miles of darkness, a signal that takes more than 17 hours just to reach Earth. And as the scientists pored over what it was sending, they kept running into things that didn't fit the textbooks. The sharpness of the boundary was the first shock, but it wasn't the biggest one. Let's talk about the temperature, because this is one of those facts that sounds completely backwards until you understand what's really going on. As Voyager approached the Heliopause, it passed through that outer region of the bubble where the solar wind, after racing outward for years, finally piles up and slows down against the boundary. And when that fast-moving solar wind slams into the wall and stalls, something has to happen to all that energy. It doesn't just disappear. The particles get compressed. They get squeezed together against the boundary. And as they pile up, they heat up. Voyager flew straight through this region and measured a layer of plasma just inside the heliopause that was blisteringly hot, far hotter than the models had predicted. Now here's where it gets counterintuitive, and I want to take a second on this because it trips a lot of people up. When scientists say this plasma is hundreds of thousands, even millions of degrees, your instinct is to picture something that would instantly vaporize the spacecraft. But that's not how temperature works out there. Temperature in physics is really a measure of how fast particles are moving. The faster they zip around, the higher the temperature. And yes, the individual particles in this region are moving incredibly fast, which technically means an incredibly high temperature. But, and this is the key, there are almost none of them. The interstellar medium is so unbelievably thin, so close to a perfect vacuum, that even though each particle is moving fast and is technically hot, there are so few of them that they carry almost no actual heat. Think of it this way. The sparks flying off a sparkler on the 4th of July can be over 1,000 degrees, but you can wave your hand right through them and feel nothing because each spark is tiny and there's so little material there. Voyager experiences the heliopause the same way. The plasma is technically scorching, but so sparse that the spacecraft sails right through, unbothered. It registers the temperature on its instruments without ever being in danger. But the fact that this region was so much hotter and denser than predicted told scientists something important. It meant the interaction between the solar wind and interstellar space is far more violent, far more energetic than anyone had assumed. The sun isn't fading gently into the galaxy, it's slamming into it. There's a genuine, powerful collision happening out there at the edge, an enormous release of energy as our star's wind crashes into the wall of the wider Milky Way. And we never would have known the true intensity of it without a spacecraft physically flying through and taking the measurement. This is the moment the heliopause stopped being a concept and became a place. Before Voyager, the edge of the solar system was a line in a diagram, a theoretical boundary with assumed properties. After Voyager, it became a real, physical structure with measurable features. It has a thickness, it has a temperature, it has a magnetic character. For the first time in human history, we could describe the edge of our solar system not as an idea, but as a thing we had actually touched. With numbers attached to it, that came from direct experience instead of equations on a whiteboard. That's a profound shift. That's the difference between believing a place exists and standing in it. And it raised an obvious next question. If the temperature was wrong in the models, and the sharpness was wrong, what else was wrong? What about the magnetic field? Because the magnetic field was supposed to be one of the clearest tells of all, and what Voyager found there might be the strangest result of the entire mission. Of all the things scientists expected Voyager to find when it crossed the boundary, the behavior of the magnetic field was supposed to be one of the most reliable, and it ended up being one of the most confusing. To understand why, we need to talk for a minute about magnetism in space, because it plays a much bigger role out there than most people realize. Everything in space is threaded with magnetic fields. The sun has one, an enormous magnetic field that gets carried outward by the solar wind, wrapping the entire heliosphere in the sun's own magnetic signature. And the galaxy has one too, a vast magnetic field that runs through interstellar space, shaped over millions of years by the movement of stars and gas across the Milky Way. These two magnetic fields, the suns and the galaxies, point in different directions. They're oriented differently, aligned along different angles in space. So here's what the scientists predicted. When Voyager crossed the Heliopause, it should feel the magnetic field suddenly change direction. On the inside, the field should be pointing one way, following the sun's orientation. On the outside, it should snap to a completely different angle, following the galaxies. That sharp change in magnetic direction was supposed to be one of the surest signs that the spacecraft had truly crossed into interstellar space. The model said the two fields would meet at the boundary at clashing angles, creating turbulence, twisted field lines, a tangled mess where the sun's magnetism collided with the galaxies. That's not what happened. When Voyager crossed over, the direction of the magnetic field on the far side was far more similar to the field on the near side than anyone expected. The magnetic field didn't snap to a dramatically different angle. It stayed roughly aligned. The sun's magnetic field and the galaxy's magnetic field were somehow pointing in nearly the same direction at the boundary. And that's genuinely strange, because there's no obvious reason they should. These are two completely separate magnetic systems with completely separate origins, and yet at the place where they meet, they seem to be lined up, almost cooperating. Scientists are still working through what this means. One leading idea is that the two magnetic fields might actually be connecting to each other at the boundary, linking up and reorganizing themselves in a way that smooths out the transition. The sun's magnetic field might be reaching out and joining hands with the galaxies in a process that physicists are still trying to fully describe. If that's true, it changes our picture of the Heliopause yet again. It's not just a wall where two regions meet. It might be a place where the sun's magnetism and the galaxy's magnetism actively merge, weaving together into a single connected structure. And this connects to something even bigger, because the magnetic surprise wasn't the only thing Voyager's plasma instruments turned up. When the spacecraft started measuring the density of the interstellar medium directly, the material it was now swimming through on the far side of the boundary, it found that the galaxy's gas was denser than scientists had estimated. There was more material out there, packed more tightly than the models had assumed. Now, that might sound like a small technical detail, but think about what it means. If the interstellar medium is denser than we thought, then it's pushing on the heliosphere harder than we thought. The galaxy is squeezing our sun's bubble more forcefully than the old models accounted for. And that helps explain something scientists had been puzzling over. The heliosphere isn't a perfect sphere. It's lopsided. It's compressed in some directions, where the galaxy presses in hardest, and stretched out in others, trailing behind the sun like a windsock as our whole solar system plows through the galaxy. The denser interstellar medium Voyager measured is part of the reason that bubble gets pushed and squashed into its strange, asymmetric shape. So put all of this together and a new picture emerges. The heliosphere is not the simple, clean, spherical bubble in the old diagrams. It's a complex, magnetized, ever-shifting structure, shaped by a constant tug of war between the sun pushing out and the galaxy pushing in. The boundary is sharp where they expected gradual, hot where they expected cool, magnetically aligned where they expected chaos, and surrounded by a galaxy that's denser and pressing harder than the math had predicted. Almost every major expectation was overturned, and the only reason we know any of it is that two spacecraft from the 1970s kept flying long enough to find out. But Voyager didn't just rewrite our picture of the boundary. It revealed something about that boundary that matters for every living thing on Earth. Because that wall out there isn't just a scientific curiosity, it's a shield. And without it, you might not be here at all. I want you to think about something you've probably never thought about in your entire life. Right now, as you're sitting there, the galaxy is trying to hit you. Not metaphorically, literally. The Milky Way is filled with radiation so powerful, so energetic, that if it reached you in full force, it would be a serious problem for every living cell in your body. And the only reason it doesn't is a bubble you can't see, blown by a star 93 million miles away, with an edge that Voyager just crossed. Let me explain what's actually out there, because most people have no idea how hostile the galaxy really is. Scattered across the Milky Way, stars are constantly dying. Some of them go out quietly, but the massive ones explode in titanic detonations called supernovae, releasing more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. And these explosions act like cosmic particle accelerators. They take ordinary particles and fling them outward at almost the speed of light. These are galactic cosmic rays, and they're screaming through interstellar space in every direction, all the time, by the trillions. A single galactic cosmic ray particle carries an astonishing amount of energy. When one of them hits something, it hits hard. It can tear straight through atoms, break apart molecules, damage DNA, scramble the delicate machinery inside living cells. In high enough doses, this kind of radiation causes cancer, damages the nervous system, and can be outright lethal. The galaxy is, to put it bluntly, soaking in the stuff. Interstellar space is bathed in a constant sleet of high-energy radiation that would be devastating to unprotected life. And here's the thing. Earth is sitting in the middle of that galaxy. So why aren't we being shredded by cosmic rays every second of the day? The answer is the heliosphere. That giant bubble the sun blows around the entire solar system doesn't just mark our territory. It actively deflects a huge fraction of those galactic cosmic rays before they ever get close to the planets. The solar wind and the magnetic field embedded in it act like a force field, batting away or slowing down a large portion of the high-energy particles trying to get in from the outside. The heliosphere is, in a very real sense, a shield, and we've been living safely inside it for the entire history of life on Earth. This is where Voyager's measurements get personal. Because remember what happened when the spacecraft crossed the Heliopause? The galactic cosmic ray count jumped. It surged upward the moment Voyager left the bubble. That spike is the shield made visible. On the inside, the cosmic rays were suppressed, held back by the sun's protection. On the outside, they came flooding in at full strength. Voyager measured directly the difference between protected space and unprotected space, and the gap between the two was sharper and more dramatic than the models had predicted. The shield, it turns out, is even more effective and more sharply defined than scientists realized. Voyager essentially gave us the first real measurement of how much protection the heliosphere actually provides. It confirmed that the boundary works like a filter, separating two completely different radiation environments. Inside, relatively safe. Outside, hostile. And the wall between them is thin and decisive, exactly the kind of crisp boundary that makes for an effective barrier. Now you might be wondering, doesn't the Earth have its own protection? And yes, it does. Earth has its own magnetic field, which deflects a lot of harmful particles and a thick atmosphere that absorbs much of the rest. Those are real important layers of defense. But they're the last two layers, the innermost shields. The heliosphere is the outermost shield, the first line of defense for the entire solar system. It's been knocking down a huge fraction of the galaxy's radiation long before any of it gets anywhere near our planet's own defenses. It's a protection system most people have never even heard of. And Voyager is the only thing that's ever let us measure it from the boundary itself. And this matters more than you might think, because that shield is not guaranteed to stay the same forever. The strength of the heliosphere depends on the sun, and the sun is not a fixed, unchanging thing. It goes through cycles, getting more and less active over time. When the sun is more active, it blows a stronger wind and inflates a bigger, tougher bubble. When it's quieter, the bubble weakens and shrinks, letting more cosmic rays slip through. So the level of protection we enjoy isn't constant. It rises and falls. And over much longer timescales, things can change far more dramatically than that. Which brings us to something genuinely unsettling that Voyager's data forces us to confront. The shield has not always been this strong, and it won't always be, because our sun, carrying all of us inside its bubble, is on a journey through the galaxy. And that journey is about to take us somewhere the heliosphere has never had to deal with before. Decode. Here's something that almost never gets talked about, and it should, because it completely changes how you think about our place in the cosmos. The sun is not standing still. None of this is standing still. Right now, you and the Earth and the sun and every planet in the solar system are hurtling through the galaxy at around 500,000 miles per hour. We are on a journey, a great loop around the center of the Milky Way that takes about 230 million years to complete one lap. The last time the sun was in the position it occupies today, dinosaurs hadn't even appeared on Earth yet. And as the sun makes this enormous journey, it doesn't travel through empty, uniform space. The galaxy is not the same everywhere. The interstellar medium, that thin gas and dust between the stars, comes in patches. Some regions are emptier, with almost nothing in them. Other regions are denser, thick with gas and dust, sometimes forming enormous clouds light years across. As the sun travels, it drifts through these different neighborhoods, sometimes through thin space, sometimes through dense space. And the density of the space around us has a direct, powerful effect on the shield protecting us. Think back to what Voyager taught us. The size and strength of the heliosphere is a balance. The sun's wind pushing out against the interstellar medium pushing in. When the stuff outside is thin, the sun's wind wins easily, and the bubble inflates large, holding the galaxy's radiation far away. But when the sun passes through a denser region, the outside pressure increases. The galaxy pushes back harder, and the bubble gets compressed. It shrinks. The shield draws in closer to the sun, and more of the galaxy's cosmic radiation is able to penetrate deeper into the solar system, closer to the planets, closer to Earth. Right now, we're actually in a relatively comfortable spot. The sun is currently traveling through a fairly empty region of the galaxy, a low-density pocket sometimes called the local bubble, which was probably carved out by supernova explosions millions of years ago. Because the space around us is so thin, our heliosphere is large and our shield is strong. We're in a good neighborhood, radiation-wise, but that's not permanent. As the sun continues its journey, it will eventually drift out of this comfortable pocket and into denser regions. And when it does, the heliosphere could shrink significantly. The shield could weaken, and more of the galaxy's radiation could reach the inner solar system than has reached it in a very long time. Now, before anyone panics, let me be clear about the timescale here. We're talking about changes that unfold over tens of thousands to millions of years, not something that's going to happen next Tuesday. This is not a threat to you, or your kids, or your kids' kids, but it's a profound thing to understand about the long-term story of life on Earth. The level of cosmic protection our planet enjoys has changed over the deep history of the Earth, and it will change again in the deep future. Some scientists have even wondered whether past encounters with dense interstellar clouds, which would have compressed the heliosphere and increased radiation, might have left fingerprints in Earth's history, possibly even playing a role in some of the climate shifts or biological changes that show up in the geologic record. That research is still ongoing and far from settled, but the very fact that we can ask the question is remarkable. And the only reason we can ask it at all is Voyager. Before these two spacecraft physically crossed the boundary and measured the real density of the interstellar medium, the real strength of the magnetic fields, the real behavior of the shield, all of this was guesswork. Now we have actual numbers. We have direct evidence of how the heliosphere responds to the galaxy around it. And that gives scientists, for the first time, a real foundation for understanding how our cosmic shield has behaved in the past and how it might behave as the sun carries us into the unknown regions ahead. Voyager didn't just measure the edge of the solar system. It gave us our first real tool for understanding our entire journey through the galaxy. But there's a more immediate reason all of this matters too. Because we're not just curious about the radiation out there. We're about to start sending people into it. For most of human history, the danger Voyager measured out at the edge of the solar system was purely abstract. Cosmic rays, interstellar radiation, the strength of the heliosphere, none of it touched daily life. But that's changing, because we are entering a new era of space exploration, one where we're planning to send human beings further from Earth than anyone has ever gone. And the moment you put a living person outside the Earth's protective layers, all of this stops being abstract and becomes a life or death engineering problem. Here's the situation. Down here on the surface, you're protected by two powerful shields. Earth's magnetic field, which deflects charged particles, and the thick blanket of the atmosphere above you, which absorbs most of the radiation that gets through. Even the astronauts on the International Space Station are still largely protected because they orbit close to Earth. Inside the reach of our planet's magnetic field, they're not fully exposed. They're still tucked behind most of our defenses. But the moon is different. Mars is very different. The moment a crew leaves the protection of Earth's magnetic field and heads out into deep space, they lose that shielding. They're exposed to the full force of the radiation environment, including those galactic cosmic rays Voyager measured pouring in from across the Milky Way. And there's no easy way to block them. These particles are so energetic that ordinary shielding doesn't stop them. In some cases, thin shielding actually makes things worse, because when a cosmic ray slams into a thin metal wall, it shatters into a spray of secondary particles, like a single bullet turning into a shotgun blast. The radiation problem is one of the single biggest obstacles standing between us and long-duration human missions to Mars. So how do you plan for a danger like that? You have to understand it. You have to be able to predict, as accurately as possible, how much radiation a crew will be exposed to, how it varies over time, and how the heliosphere shapes and reduces it before it ever reaches them. And this is exactly where Voyager's measurements become priceless. By directly measuring how the heliosphere filters galactic cosmic rays, how the shielding changes near the boundary, and how the radiation environment actually behaves, Voyager gave scientists real data to build better models. Models that mission planners now use to figure out how to protect astronauts, how thick to make shielding, how to time missions, how to keep human beings alive on journeys that will last years and carry them far beyond the safety of Earth. Think about that for a second. A spacecraft designed in the early 1970s, before anyone seriously imagined sending humans to Mars, is now contributing to the safety calculations for missions that haven't even launched yet. The engineers who built Voyager couldn't have known that their machine would one day help protect astronauts walking on another world. But that's exactly what's happening. The data Voyager is sending back from interstellar space is feeding directly into how we'll keep future explorers safe. The oldest spacecraft we have is helping plan the newest missions we'll ever attempt. And it goes beyond just the missions we're planning now. Understanding the radiation environment of deep space is fundamental to every dream we have about becoming a spacefaring species. Long-term outposts on the moon, permanent settlements on Mars, crewed missions to the asteroids and beyond. Every single one of those futures depends on solving the radiation problem, and every solution starts with understanding the environment, which starts with the measurements, which for the region beyond the heliosphere means Voyager. These two spacecraft are quietly laying groundwork for a future they'll never see, sending back the numbers that the next generations of explorers will depend on. But here's the frustrating part, and it's also the exciting part. Voyager was never designed for this. Its instruments are over 40 years old. It was built to photograph planets, not to map the magnetic structure of interstellar space. And the fact that it's revealed so much with such primitive tools is making scientists hungry for something more. Because if a 40-year-old spacecraft, half blind and running on fumes, could overturn this much of what we thought we knew, imagine what a purpose-built explorer could find. Voyager's discoveries have done something interesting to the scientific community. They've created a kind of itch, a frustration, because every answer Voyager sent back came wrapped in 3 new questions, and the spacecraft simply doesn't have the tools to answer them. It's like being handed a single blurry photograph of an undiscovered country and being told that's all you get. You can see enough to know the place is extraordinary. You can't see enough to understand it. And that gap between what we've glimpsed and what we want to know is driving one of the most exciting conversations in space science today. The case for a dedicated interstellar mission. Think about Voyager's limitations for a moment. It carries instruments designed in the 1970s with the technology of that era. It crossed the boundary in just one spot, along one single path out of the entire vast surface of the heliosphere. It's like trying to understand an entire coastline by wading into the ocean at exactly one beach. You learn a lot about that one spot, but you have no idea how representative it is. Is the boundary the same thickness everywhere? Does the magnetic field behave the same way in other directions? Is the interstellar medium denser here than it is somewhere else? Voyager can't tell us. It only went through once, in one place, with tools built before the internet existed. So scientists have begun seriously designing what a real interstellar mission could look like. Imagine a spacecraft built from the ground up specifically to explore beyond the Heliopause, equipped with modern instruments, sensors orders of magnitude more sensitive than anything Voyager carries, a probe that could measure the magnetic fields, the particle flows, the density and the chemical makeup of interstellar space in extraordinary detail across a whole range of distances as it traveled outward. Instead of one blurry snapshot, we'd get a rich, detailed map of the boundary and the space beyond it. We could finally understand the Heliopause not as a single crossing point, but as the complex, three-dimensional structure it really is. Such a mission would be designed to travel faster than Voyager, to reach the boundary in less time, and then push much deeper into interstellar space than Voyager ever will. It could study the shape of the heliosphere from the outside, mapping how our bubble plows through the galaxy, how it's compressed in front and stretched out behind. It could sample the pristine interstellar medium directly, the actual raw material of the galaxy, gas and dust, that has never been touched by our sun's influence. It could look back at the heliosphere and see it whole, the way you can only understand the shape of a house by stepping outside and walking around it. We have never seen our own cosmic bubble from the outside. A dedicated mission could give us that view for the first time. Of course, a mission like this is a monumental challenge. The distances are staggering. Even traveling fast, it would take decades just to reach the boundary, and the people who launched it might not live to see its most important discoveries. It's the kind of project that requires patience measured in generations. Scientists handing the mission off to their students, and their students to theirs. But that's exactly what makes it so profound. It's an act of faith in the future. A bet that the knowledge is worth waiting for, even if you won't be the one to receive it. The original Voyager team understood that. Many of the people who launched these spacecraft in 1977 are no longer with us, but the machines they built are still out there, still working, still teaching us. A future interstellar mission would carry that same spirit forward. And the urgency is real because Voyager won't last forever. In fact, the most poignant part of this entire story is what's happening to the two spacecraft right now, as we speak. Because after nearly half a century of flight, these two faithful explorers are slowly, gracefully running out of life. And the way they're spending their final years tells you everything about why this mission has captured the hearts of so many people around the world. Chapter 10: The Long Goodbye. There's something happening out there right now that I find genuinely moving, and I think you will too. The two Voyager spacecraft are dying, slowly, gracefully, and the people who care for them are doing everything they can to keep them alive just a little longer, fighting for every extra month of life, every last bit of data, from machines that have already given us more than anyone ever dreamed. Remember how the Voyagers are powered, not by solar panels, which are useless this far from the sun, but by the slow radioactive decay of plutonium. And the thing about radioactive decay is that it's relentless, and it only goes one direction. Every year, that power source produces a little less electricity than the year before, It's been fading since 1977, and it cannot be refueled, cannot be recharged, cannot be reversed. The spacecraft are running on a battery that has been draining for nearly 50 years, and there is no way to stop it. For a long time, this wasn't an urgent problem. There was plenty of power for everything. But now, after all these decades, the available electricity has dropped so low that the engineers face an agonizing set of choices. There isn't enough power to run all the instruments anymore. So, one by one, they've had to make decisions about what to turn off, which instruments to sacrifice, which parts of the spacecraft to let go cold and dark forever, in order to keep the most important systems running just a little longer. This is happening right now. The team managing the Voyagers has been carefully, deliberately shutting down systems, heaters, instruments, anything non-essential to conserve the dwindling trickle of power. It's a kind of triage performed across billions of miles of space on a spacecraft so far away that a single command takes the better part of a day just to arrive. The engineers are essentially nursing 2 elderly patients through their final years, making every hard call necessary to extend their lives, knowing that each shutdown is permanent and that the end, eventually, is coming. And here's what gets me about it. They're doing this so that the Voyagers can keep transmitting from interstellar space for as long as humanly possible. Every instrument they keep alive sends back a little more data about that region beyond the Heliopause that we've never been able to sample any other way. Every extra year is another year of measurements from a place no other spacecraft will reach for decades, maybe longer. So the team fights for every scrap of life, not out of sentiment, though there's plenty of that, but because these dying machines are still, even now, the only eyes we have in interstellar space. But the sentiment is real too. These spacecraft have become something more than instruments to the people who work with them, and to millions of people around the world who have followed their journey. There's something about them. 2 small, fragile machines launched before most of us were born that have traveled further than anything humanity has ever made, still calling home across the unimaginable dark, their voices growing fainter every year. It's impossible not to feel something for them. They are, in a strange way, our representatives, the furthest reach of human curiosity, still pushing outward into the night. Eventually, sometime in the coming years, the power will drop too low to run even the most basic systems. The signals will stop, and the Voyagers will fall silent, becoming dark, cold, drifting monuments, coasting outward through the galaxy forever. But here's the beautiful part. They won't stop moving. Even after the last signal fades, even after we lose contact for good, the Voyagers will keep going. They'll keep flying outward, deeper and deeper into interstellar space, carrying with them something extraordinary. A message meant for whoever or whatever might find them in the unimaginable future. And that message might be the most haunting thing humanity has ever created. Chapter 11, A Message in a Bottle, Thrown into the Galaxy. Bolted to the side of each Voyager spacecraft is a golden phonograph record, and the story of what's on that record and why it's there is one of the most beautiful things our species has ever done. When the Voyagers were being built, a team of people, led by the astronomer Carl Sagan, were given a strange and wonderful assignment. The spacecraft were going to leave the solar system and travel through the galaxy, essentially forever. Long after the sun itself burns out, the Voyagers will still be drifting through interstellar space, more or less intact, because out there in the vacuum, there's almost nothing to erode them. They are, in effect, time capsules that will outlast the Earth itself. So the team asked a profound question. If these objects are going to wander the galaxy for billions of years, shouldn't they carry something? A message? A record of who made them? And so they created the Golden Record, a gold-plated copper disc designed to last 1 billion years or more, carrying a portrait of life on Earth, intended for any intelligence that might one day find it. They had to imagine the impossible. How do you communicate with a mind that shares no language with you, no culture, no biology, a mind that might not even exist yet, that might not be found for 1 billion years? What do you put on a message to the universe itself? What they chose is breathtaking. The record contains sounds of Earth, the wind, rain, thunder, the sounds of animals, birds, whales singing in the deep ocean. It carries human voices, greetings spoken in 55 different languages, from ancient tongues to modern ones. A chorus of humanity saying hello to the cosmos. It contains the sound of a human heartbeat, a mother's first words to her child, laughter. It carries music from across the world and across the ages, the work of great composers alongside folk songs and traditional melodies, an attempt to capture the full breadth of human creativity in a handful of recordings. And it carries images encoded onto the record, pictures of Earth, of human beings, of our cities and our landscapes and our science, a visual portrait of our world and ourselves, instructions included on the cover for how to decode and play the whole thing, etched in symbols that the team hoped any sufficiently advanced intelligence might one day figure out. They even included a map, a way of locating our sun among the stars, so that whoever finds the record might know where it came from, a return address on a message to the universe. Now, let's be honest about the odds. Space is almost incomprehensibly vast and almost incomprehensibly empty. The chance that either Voyager will ever be found by another intelligence is staggeringly, almost unimaginably small. The spacecraft will most likely drift for billions of years and never come near another star system, never be discovered, never be played. The Golden Record may never reach a single set of eyes or ears other than our own. The people who made it knew that. They weren't naive about the odds, but that's exactly what makes it so profound. The Golden Record was never really only about being found. It was about who we are. It was an act of hope, of optimism, of reaching outward into the dark with open hands. It was humanity saying, we were here, we existed. We looked up at the stars, and we wondered, and we made these beautiful, fragile machines, and we sent them out to carry our story into eternity. whether anyone ever receives that message or not. The act of sending it says something noble about us. In a universe that is mostly cold and silent and empty, a small species on a small planet chose to introduce itself to the cosmos just in case anyone was listening. And so the Voyagers carry that message outward, even now, even as their power fades. When the last signal goes silent and we lose them forever, they'll still be out there, still carrying that golden message. 2 bottles thrown into the cosmic ocean. Drifting towards stars they'll reach in tens of thousands of years. They will outlast every one of us. They will outlast our civilization. They will, in all likelihood, outlast the Earth itself. And they'll carry the memory of us, the sound of a heartbeat, a greeting, a song, into a future so distant we can barely imagine it. Chapter 12. What's actually out there? So Voyager has crossed the boundary. It's in interstellar space now, the real space between the stars. And I think it's worth stopping to ask a simple question that turns out to have a deeply strange answer. What is that space actually like? When you finally leave the sun's bubble and enter the galaxy proper, what surrounds you? Because the honest answer is nothing like what most people picture. And understanding it changes how you see our entire place in the cosmos. When we say Voyager entered interstellar space, your mind probably conjures something dramatic. A starfield maybe, glittering all around. Or some kind of visible barrier, a curtain that the spacecraft pushed through. But the reality is far stranger and far emptier than that. Interstellar space is, by any human standard, the most profound emptiness imaginable. The material that fills it, that interstellar medium we keep talking about, is so thin that it makes the best vacuum we can create in a laboratory on Earth look crowded by comparison. We're talking about, on average, a tiny handful of atoms in a space the size of a room. If you were floating out there where Voyager is, you would see nothing nearby. No glow, no nearby objects, no sense of having crossed into anywhere at all. Just darkness and the distant stars unchanged. And yet paradoxically, this near-perfect emptiness is not truly empty, and that's the whole point. It's filled with structure you can't see. It's threaded with magnetic fields, the galaxy's own magnetism, running through the void. It's washed with those high-energy cosmic rays, sleeting in from distant supernovae. It has a faint, thin gas, mostly hydrogen left over from the birth of the galaxy and enriched by generations of dying stars. It has whispers of dust, microscopic grains forged in the atmospheres of ancient suns. Interstellar space looks like nothing, but it's actually a vast, active medium, a sea of energy and particles and fields. And Voyager is the first thing we've ever built that's been able to dip its instruments directly into that sea and tell us what it's made of. One of the most fascinating things Voyager detected out there wasn't something it saw, but something it heard. Or rather, something its instruments could translate into sound. Voyager carries a plasma wave instrument designed to detect vibrations in the thin gas of interstellar space. And out there, in the emptiness, it picked up a faint, persistent hum, a steady, eerie tone, the vibration of the interstellar medium itself, ringing ever so slightly as the spacecraft drifts through it. Scientists have actually converted these measurements into audio you can listen to, and it's haunting. It's the sound of the space between the stars, a region that humanity had theorized about for centuries, suddenly given a voice. For the first time, we could hear what interstellar space sounds like. And it sounds like a low, steady, lonely hum in the dark. That hum told scientists something useful too. The pitch of it depends on the density of the gas around the spacecraft. By listening to how that tone changed, researchers could measure the density of the interstellar medium directly, and that's part of how they discovered it was denser than expected. The galaxy was, quite literally, singing the answer, and Voyager's antique instruments were just barely able to pick up the tune. There's something almost poetic about that. A spacecraft from the 1970s listening to the song of the galaxy and translating it back to us across 11 billion miles. But here's a detail that puts the whole journey in perspective, and it's a humbling one. Even though Voyager has crossed the Heliopause and entered interstellar space, it is nowhere near leaving the sun's gravitational influence entirely. The sun's gravity reaches out far, far beyond the Heliopause, holding on to a vast, distant cloud of icy objects that surrounds the entire solar system in a gigantic sphere. And to get through that, to truly leave the sun's reach behind, Voyager would have to travel for tens of thousands of years more. So while Voyager has crossed an enormous and meaningful boundary, the edge of the sun's wind, it's still, in a gravitational sense, deep in the sun's backyard. The solar system, when you measure it by the sun's gravity rather than its wind, is so unbelievably vast that even our fastest, furthest spacecraft has barely begun to cross it. That's the thing about all of this. Every answer Voyager gives us comes attached to a humbling reminder of scale. We crossed the edge, yes, but there are bigger edges beyond it. We measured the boundary, yes, but it's just one boundary among several ways of defining where home ends. The deeper Voyager goes, the more clearly we see just how small our reach really is, and just how enormous the space around us truly extends. And that's not discouraging. It's the opposite. It means there is so much more out there to find, so much more space to explore. We've taken one step past the threshold, and the universe beyond that threshold is bigger than we ever fully grasped. Chapter 13. How one spacecraft rewrote the map. Let's step back and take stock of everything Voyager actually changed, because when you line it all up in one place, the scope of it is genuinely staggering. This is a spacecraft that was supposed to photograph some planets and then go quiet. Instead, it quietly rewrote our understanding of where we live in the universe. So let's count the ways. Before Voyager, the edge of the solar system was a guess. A reasonable guess, backed by good physics, but a guess all the same. We thought we knew roughly where the Heliopause was. We thought we knew what it would be like to cross it. We had built careful models, and we had a lot of confidence in them. And then Voyager arrived at the boundary and showed us that we'd gotten the details wrong, over and over again. The transition that was supposed to be wide and gradual turned out to be sharp and sudden. The region that was supposed to be cool turned out to be searingly hot. The magnetic fields that were supposed to clash at violent angles turned out to be strangely aligned. And the interstellar medium that was supposed to be a certain thinness turned out to be denser, pressing harder on our bubble than we'd assumed. Almost every major prediction needed revising once Voyager delivered the real numbers. And think about what that means more broadly. It means that even with all our science, all our computing power, all our sophisticated theories, the universe still has the capacity to surprise us completely. We had spent decades building a picture of the boundary, and a 40-year-old spacecraft flew through it and showed us that reality was stranger than our best models. That's not a failure of science. That's science working exactly as it should. We made our best predictions, we went and checked, and we updated our understanding based on what we actually found. The boundary went from being a line in a textbook to being a real, physical, measurable structure with a temperature and a thickness and a magnetic personality all its own. That transformation from theory to touched reality is one of the great quiet achievements in the history of exploration. Voyager also fundamentally changed our understanding of the heliosphere as a protective system. Before these spacecraft crossed over, we suspected the sun's bubble shielded us from cosmic radiation, but we couldn't measure the effect directly. Voyager gave us that measurement. It showed us, in hard data, the difference between protected space and unprotected space, and revealed that the shield is sharper and more effective than we knew. It transformed our understanding of the heliosphere from an abstract idea into a concrete, life-relevant fact. We now know, with real numbers, that there's a barrier out there knocking down a huge fraction of the galaxy's radiation before it can reach us. That's not philosophy. That's a measured physical reality, and we owe that knowledge to 2 aging spacecraft. And perhaps most importantly, Voyager changed the questions we're asking. Before, the big question was simply, where does the solar system end? Voyager answered that, and in doing so, opened up a dozen new questions we didn't even know to ask. Why is the boundary so sharp? Why are the magnetic fields aligned? How does the heliosphere change as the sun moves through the galaxy? What does the boundary look like in other directions? How has our shield varied across the deep history of life on Earth? These are the questions driving the next generation of space science, and none of them would exist in their current form without Voyager. The spacecraft didn't just give us answers. It gave us better questions, which is, in many ways, the more valuable gift. There's a lesson buried in all of this that goes beyond astronomy. Voyager is a story about what happens when you keep going. The planetary mission was the plan, the headline, the thing everyone got excited about. But the most profound discoveries came afterward, in the decades of quiet flight that nobody initially cared about, when the spacecraft were just coasting outward through the dark with their cameras off. The real revelations came not from the flashy planetary flybys, but from patiently traveling into the unknown, year after year, instrument by instrument, waiting for the moment of crossing. There's something deeply human in that. The biggest discoveries often come not from the part of the journey you planned, but from having the patience and the curiosity to keep going past the point where you thought the story was over. Chapter 14, The Neighborhood We're Drifting Through. I want to come back to something we touched on earlier, because it deserves a much deeper look. The sun is moving through the galaxy, carrying all of us with it, and the neighborhood it's drifting through has a story of its own. A story written in gas and dust and ancient explosions, and Voyager's measurements are finally letting us read it. Let's start with where we are right now. As I mentioned, our solar system is currently passing through a remarkably empty pocket of the galaxy. Astronomers call it the local bubble, and it's exactly what it sounds like. A vast, low-density cavity in the interstellar medium, hundreds of light years across, where the gas is thinner than in the surrounding regions of the Milky Way. And the origin of this bubble is genuinely dramatic. Scientists believe it was carved out by a series of supernova explosions, ancient stars that died in titanic blasts millions of years ago. Those explosions blew the gas outward, sweeping it up and pushing it away, leaving behind the relatively empty cavity that our sun happens to be passing through right now. We are, in a very real sense, traveling through the hollowed-out wreckage of stars that died before humans existed. And because we live in this low-density bubble, our heliosphere is large and our shield is strong. The thin gas around us doesn't push very hard on the sun's wind, so the bubble inflates to an enormous size, holding the galaxy's radiation comfortably far away. We are, cosmically speaking, in a pretty pleasant spot. But here's where Voyager's data and ongoing research get interesting, because even within this bubble, the picture isn't uniform. The sun is actually currently moving through a small wisp of slightly denser gas. Within the larger bubble, a cloud sometimes called the local interstellar cloud. And it's been suggested we may be near the edge of it, possibly drifting toward yet another cloud beyond. The interstellar environment, it turns out, has texture and structure even on these relatively small scales, and our sun is constantly sailing from one patch into another. Now think about what that means over deep time. The sun has been traveling for 4.5 billion years. It has passed through countless different regions of the galaxy, some empty, some dense, some calm, some violent. There have almost certainly been times in Earth's history when the sun plunged into a dense, interstellar cloud, far denser than anything around us now. And when that happened, the physics Voyager taught us tells us exactly what would have followed. The dense gas would have pressed in hard on the heliosphere, compressing it, shrinking our shield, possibly even pushing the boundary closer to the sun than the orbit of the outer planets. And with the shield compressed, far more galactic cosmic radiation would have penetrated into the inner solar system, reaching Earth in much greater quantities than it does today. What would that have meant for life? This is where the science gets speculative, but fascinating. A significant increase in cosmic radiation could affect Earth's atmosphere, its climate, even the rate of genetic mutation in living things. Some researchers have explored whether past encounters with dense clouds might have left traces in the geologic record, subtle fingerprints in the form of certain isotopes that get produced when cosmic rays bombard the atmosphere. There are even hypotheses, still very much debated, that such encounters might have contributed to ice ages or to shifts in the patterns of life over the long history of our planet. None of this is settled science, and I want to be careful not to overstate it. But the underlying physics is sound. We know the heliosphere responds to the galaxy around it, because Voyager measured exactly that response at the boundary, and we know the galaxy around us changes as the sun travels. So the conclusion is hard to escape. The level of cosmic protection Earth has enjoyed has not been constant across its history, and the story of life on this planet may be woven in ways we're only beginning to understand into the story of our sun's journey through the galaxy. And it works the other way too. Just as we've passed through denser regions in the past, we'll pass through them again in the future. As the sun continues its endless loop around the galactic center, it will eventually leave this comfortable local bubble behind and drift into denser territory once more. When that happens, far in the future, our heliosphere will shrink, our shield will weaken, and the radiation environment of the inner solar system will change. It's not a danger for any of us, or for many, many generations to come, but it's a reminder that nothing about our cosmic situation is permanent. The comfortable, well-shielded pocket of space we live in today is a temporary arrangement, a lucky stretch of calm in a long and ever-changing journey. And the only reason we can even begin to understand what those past and future transitions look like is that 2 spacecraft flew out to the edge and measured how the boundary actually behaves. Chapter 15. Are we special, or is everyone out there too? Here's a question that Voyager's discoveries naturally lead to, and it's one of my favorites because it expands the whole story from being about our sun to being about every star in the galaxy. If our sun blows a protective bubble around itself, do other stars do the same thing? And the answer, it turns out, is yes. And that has profound implications for one of the biggest questions we can ask. Are we alone? Let's think it through. The heliosphere exists because the sun blows a wind of charged particles outward, and that wind pushes back against the interstellar medium to carve out a bubble. But the sun isn't unique in blowing a wind. Most stars do it. They all shed particles from their surfaces, streaming material outward into space. And that means most stars should carve out their own protective bubbles, their own versions of the heliosphere. Astronomers call these astrospheres. The general term for the bubble a star blows around itself. Our heliosphere is just our local example of a phenomenon that's probably happening around stars all across the galaxy. And astronomers have, in fact, detected the signatures of these astrospheres around other stars, glimpsing the bubbles of distant suns plowing through interstellar space. Now here's why this matters so much for the question of life elsewhere. If a star's astrosphere acts as a shield, deflecting harmful galactic radiation, then the strength of that shield could be one of the factors that determines whether a planet around that star is hospitable to life. A star with a strong, healthy astrosphere would protect its planets from a significant fraction of the galaxy's cosmic radiation, just as our heliosphere protects us. A star with a weak astrosphere, or one passing through a particularly dense region of the galaxy, might leave its planets far more exposed. Suddenly, the bubble Voyager just crossed isn't just about us. It's a clue to one of the conditions that might make a world livable anywhere in the cosmos. And this connects to a broader idea that scientists take very seriously: the notion of a galactic habitable zone. You've probably heard of the habitable zone around a star, the region where temperatures allow liquid water to exist. But there may also be a habitable zone within the galaxy itself, a region where conditions are favorable for life, too close to the violent, radiation-soaked center of the galaxy, and a star system might be bombarded with too much radiation and too many disruptive events for complex life to develop, too far out toward the galaxy's edge, and there might not be enough of the heavy elements needed to build rocky planets and living things in the first place. Somewhere in between is a sweet spot. And here's the remarkable thing: our sun sits comfortably within that favorable zone, in a quiet stretch of a spiral arm, neither too close to the chaos of the center, nor too far out in the barren edge. We are, in multiple senses, living in a good neighborhood. So when you put it all together, a picture emerges that's both humbling and hopeful. Our heliosphere, the bubble Voyager just crossed, is not a freak occurrence. It's one example of a universal phenomenon. Stars protecting their planets all across the galaxy, and the conditions that make our solar system livable, the strength of our shield, our position in the galaxy, the calm pocket of space we're traveling through, may be replicated around countless other stars. If protective bubbles are common, and good galactic neighborhoods are common, then the conditions for life might be far more widespread than we once feared. We don't know yet whether anyone else is out there, but Voyager's journey to the edge has taught us that at least one of the ingredients for habitability, the protective bubble, is probably not rare at all. There's something poetic about that when you think about it alongside the golden record. Voyager carries a message meant for other intelligent life, flung outward into a galaxy that might be full of stars blowing their own protective bubbles around their own potentially living worlds. The same mission that's teaching us how common the conditions for life might be is also carrying our introduction to whatever life might be out there. The spacecraft is, all at once, our scientist and our ambassador, measuring the galaxy's hospitality while delivering humanity's hello. Whether or not anyone is ever there to receive it, the gesture captures something essential about why we explore at all. So, the Voyagers are out there, drifting through interstellar space, slowly running out of power, and eventually their signals will stop, and will lose contact forever. But the spacecraft themselves don't stop, they keep going. And that raises one of the most wondrous questions in this entire story. Where are they actually headed? When you throw a bottle into the cosmic ocean, where does the current take it? The answer stretches the imagination almost to its breaking point. Let's start with the speed, because it's genuinely hard to wrap your head around. The Voyagers are moving at roughly 35,000 miles per hour relative to the Sun. That is blisteringly fast by any earthly standard. At that speed, you could circle the entire planet in well under an hour. These are among the fastest objects humanity has ever made. And yet, here's the humbling part. Even at that incredible velocity, the distances between stars are so vast that the Voyagers will take tens of thousands of years just to travel the distance to the nearest stars. Speed means almost nothing against the emptiness of the galaxy. The fastest thing we've ever built, moving at tens of thousands of miles per hour, will still need geological stretches of time to cross even the smallest cosmic gaps. That's how big space is. That's the scale we're dealing with. So where are they going? Voyager 1 and Voyager 2 are heading in different directions, on different paths, out of the solar system, and each will have its own series of distant, slow-motion encounters with the stars. But none of these are collisions, or even close approaches in any everyday sense. When astronomers say a Voyager will approach a star, they mean it will pass within a couple of light years of it, still an enormous distance, tens of trillions of miles. The spacecraft aren't aimed at anything. They're simply drifting outward, and the galaxy's stars are slowly moving too. And over tens of thousands of years, the paths will occasionally bring a Voyager into the rough vicinity of another sun. Consider just how far into the future these encounters lie. In around 40,000 years, one of the Voyagers will pass within a couple of light years of a small dim star, drifting silently by in the dark. 40,000 years. To put that in perspective, 40,000 years ago, the last ice age was still gripping the planet, and our ancestors were painting on the walls of caves. The entire span of recorded human history, every empire, every war, every invention, every story ever written, fits many times over inside the gap between now and Voyager's next stellar encounter. And that encounter is just the beginning. The spacecraft will keep going for hundreds of thousands of years, for millions of years, drifting from the vicinity of one star to another, looping through the galaxy on a journey with no destination and no end. And here's what truly stretches the mind. The Voyagers will almost certainly outlast the Earth itself. Billions of years from now, when our sun has swollen into a red giant and possibly swallowed or scorched the inner planets. When the Earth as we know it is gone, the Voyagers will still be out there, drifting, intact, because in the near-perfect vacuum of interstellar space, there's almost nothing to erode them. No air, no water, no weather, nothing to wear them down. The occasional micrometeorite might ding them over the eons, but essentially they will remain as they are, perfectly preserved, for an almost unimaginable length of time. These two machines, built by human hands in the 1970s, may well be the longest lasting artifacts our species ever creates. Long after every building has crumbled, every monument has eroded, every trace of our civilization on Earth has vanished, the Voyagers will still be sailing through the galaxy, carrying their golden records, the last enduring evidence that we were ever here. Think about that the next time you feel small or temporary. We made something that will outlast our entire world. Two somethings. They carry the sound of a human heartbeat, greetings in dozens of languages, music, laughter, the image of a mother and child, and they will carry all of that intact through a future so vast that the lifespan of our planet is just a chapter within it. When we are gone, when everything we know is gone, the Voyagers will still be telling the universe that once, on a small blue world, there lived a curious species that looked up at the stars and decided to go. For all that Voyager revealed, I don't want to leave you with the impression that we've got the edge of the solar system figured out. Far from it. In some ways, Voyager raised more mysteries than it solved, and those open questions are where the real frontier lies. So let me walk you through some of the things we still genuinely don't understand, because the unsolved parts are every bit as thrilling as the answers. Start with the shape of the heliosphere itself. You'd think we'd know the basic shape of our own cosmic bubble, but we don't, not for certain. For a long time, the standard picture was that the heliosphere looks something like a comet, a rounded bubble on the side facing the direction of our travel through the galaxy, with a long tail streaming out behind like the wake of a boat. It's an intuitive picture, and for years it was the consensus. But then some scientists, analyzing data, including measurements related to the Voyager mission, proposed something radically different. They suggested the heliosphere might not have a long tail at all. Instead, they argued it might be shaped more like a croissant or a deflated crescent, a compact, rounded form without the dramatic trailing tail. And this isn't a settled debate. Researchers are still arguing about it. We have sent 2 spacecraft beyond the boundary, and we still don't know the basic shape of the very bubble we live inside. That's how hard this is. That's how much is left to learn. Then there's the magnetic mystery we talked about earlier, the strange alignment of the sun's magnetic field and the galaxies at the boundary. We still don't fully understand why they line up the way they do. The leading idea that the fields are connecting and reorganizing is plausible, but the details are murky. What exactly is happening at that boundary magnetically remains one of the genuine puzzles of the mission. The 2 Voyagers gave us tantalizing measurements, but each spacecraft only sampled one path through the boundary, and you can't fully map a complex magnetic structure from 2 narrow lines through it. We've seen enough to know something fascinating is going on. We haven't seen enough to explain it. And then there's perhaps the biggest open question lurking at the edge of the solar system, a hypothetical world that may or may not exist out there in the dark. For years, some astronomers have suspected there might be an undiscovered planet in the far outer solar system, a world several times the mass of Earth, orbiting the sun at a tremendous distance, far beyond Pluto, far beyond anything we've directly seen. The evidence for it is indirect. Certain distant icy objects in the outer solar system have orbits that seem strangely clustered, tilted and aligned in ways that are hard to explain by chance. Some scientists argue that the gravity of a large hidden planet could be shepherding those orbits into their peculiar pattern. Others think the clustering might be an illusion or explainable by other means. The proposed world has never been found. despite extensive searching. It remains hypothetical, a ghost inferred from the gravitational whispers of distant objects. But if it's real, it would mean there's an entire planet in our own solar system that we've never seen, lurking in the deep cold beyond everything we know. And Voyager, for all its travels, is nowhere near where such a world would be. The outer solar system, it turns out, may still be hiding enormous secrets right in our own cosmic backyard. These open questions are not failures, they're invitations. Every one of them is a reason to keep exploring, to build that next interstellar mission, to keep our telescopes scanning the outer dark, to keep listening to the faint signals from our two aging ambassadors. Science doesn't end when you cross a boundary. Crossing the boundary just shows you how much more boundary there is. Voyager pushed back the edge of the unknown, and in doing so, revealed that the unknown is far larger than we'd imagined. We answered the question of where the solar system ends, and discovered 10 new questions waiting on the other side of that answer. That's not the end of the story. That's the promise that the story continues. And maybe that's the most important thing Voyager has to teach us. Not any single fact about the boundary or the magnetic fields or the radiation, but the deeper truth that the universe is endlessly, gloriously deep. That no matter how far we travel, no matter how much we learn, there's always more. A bigger edge beyond the edge. A stranger mystery behind the mystery. The cosmos doesn't run out of wonders. We just keep finding new ones, every time we're brave enough to keep going. We've talked a lot about the spacecraft, but I want to spend a little time on the human beings behind them, because their story is just as remarkable, and it's a part most people never hear. Because keeping a 50-year-old spacecraft alive across 11 billion miles of space is not something that just happens. It takes people. Devoted, brilliant, patient people. And some of them have been doing this for their entire careers. Think about the strangeness of the job for a moment. Somewhere on Earth, there are engineers whose daily work involves communicating with a machine that is further away than anything humans have ever touched. When they send a command to Voyager, that command travels outward at the speed of light, and it still takes the better part of a day to arrive. Then, if they want to know whether it worked, they have to wait another full day for the answer to come back. A simple back and forth, a question and its response. Takes around a day and a half. There is no real-time control. There is no quick fix. Every single instruction has to be planned with extraordinary care, because by the time you find out whether it worked, the situation may already have changed. It's like trying to perform surgery through the mail on a patient who's drifting further away every second, and the signal itself is almost impossibly faint. By the time Voyager's transmission crosses 11 billion miles and reaches Earth, the power of that signal is unbelievably weak. A whisper so quiet, it defies belief. To catch it, NASA uses enormous radio antennas, dishes the size of buildings, scattered around the globe, so that at least one is always facing the right part of the sky as the Earth turns. These giant ears strain to pick up Voyager's faint voice out of the cosmic noise, and the fact that they can do it at all, that we can still hear a 1970s spacecraft whispering from interstellar space, is one of the quiet engineering miracles of our time. Every time a Voyager signal is successfully received, it's a small triumph over distance and physics and the relentless fading of an ancient machine. Then there are the people who actually understand how the Voyagers work. And this is where the story gets genuinely poignant. The spacecraft were designed and built half a century ago, using technology, programming languages, and engineering approaches that are now almost extinct. The computers aboard Voyager are programmed in ways that virtually no young engineer learns anymore. The knowledge of how these systems work, the deep, intimate understanding of their quirks and their wiring and their software, lives in the minds of a small and shrinking group of veteran engineers, some of whom have worked on the mission for decades. As they retire, there's a real challenge in passing that knowledge on. NASA has had to work to preserve old documentation, to keep the expertise alive, to make sure that when a problem arises on a spacecraft built before the engineer handling it was born, someone still knows what to do, and problems do arise. Even recently, the Voyagers have thrown their caretakers genuine scares. There have been moments when a spacecraft started sending back garbled, nonsensical data, when communication faltered, when it seemed like the end might finally have come. And each time, the team has had to play detective across 11 billion miles, diagnosing a fault they can't see, on hardware they can't touch, sending careful commands into the dark, and waiting a day and a half to see if their fix worked. And time and again, they've pulled it off. They've coaxed the old machines back to health, recovered the data stream, kept the mission alive a little longer. It's some of the most extraordinary remote troubleshooting ever performed, and it happens with relatively little fanfare. A small team quietly working miracles to keep humanity's furthest travelers talking to home. There's something deeply moving about this devotion. These engineers know how the story ends. They know the power is fading and that one day, no matter what they do, the Voyagers will fall silent. They're not working to save the spacecraft because the spacecraft can't be saved forever. They're working to honor them, to squeeze every last drop of science, every last day of contact, every last whisper from the edge, out of two machines that have given humanity more than anyone had any right to expect. It's a labor of love in the truest sense. And when the day finally comes that the last signal fades and the Voyagers go quiet for good, you can be sure there will be people on Earth who feel it like the loss of an old friend. Because that's what these spacecraft have become, not just to the engineers, but to all of us. Companions on a journey. Proof of what we can do when curiosity and dedication meet. So let's pull back, all the way back, and ask the question that sits underneath this entire story. Why? Why did we build these spacecraft? Why do we keep them alive? Why do we spend so much effort, so much ingenuity, so much of our brief time on this planet trying to understand a boundary 11 billion miles away that doesn't put food on anyone's table or money in anyone's pocket? Why do we go? It's a fair question, and people ask it about space exploration all the time. There are very practical answers, and we've covered some of them. Understanding the radiation environment helps us protect future astronauts. Understanding the heliosphere helps us understand our place in the galaxy and the long-term story of life on Earth. The technologies developed for missions like Voyager ripple outward into countless other applications. These are real, tangible benefits, and they matter. But if I'm being honest, I don't think they're the real reason. I don't think they're why a team of people in the 1970s poured their hearts into building 2 machines to fly to the edge of everything. I don't think practical benefit is what makes a person devote their entire career to keeping an old spacecraft alive. The real reason is something deeper, something that has been part of our species since the very beginning. We are explorers. It's written into us. The same drive that pushed our ancestors out of Africa and across every continent, that sent them paddling across open oceans to islands they couldn't see, that drove them to cross deserts and climb mountains and walk into the unknown, again and again, throughout all of human history. That same drive is what sent Voyager to the edge of the solar system. We go because we have always gone. We go because there is a horizon, and we cannot bear not to know what's beyond it. We go because being human means wondering, and wondering eventually means going to see for yourself. There's a famous photograph that captures this better than any words can. As Voyager 1 was leaving the solar system, before its cameras were turned off forever, it was commanded to turn around and take one last picture, looking back at the home it was leaving behind. And in that image, from billions of miles away, the Earth appears as a single point of light, not a world, not a globe of oceans and continents and forests, just a tiny dot, a pale speck, smaller than a single pixel, suspended in a beam of scattered sunlight, almost lost in the vastness. Everything that has ever happened to every human being who has ever lived, every birth and death, every love and war, every triumph and heartbreak, all of it took place on that one tiny dot. From the edge of the solar system, our entire world is just a mote of dust, hanging in a sunbeam. That image humbles you. It should. It tells you in a single glance how small we are, how fragile, how alone, drifting on our little speck through an ocean of darkness. But here's the part that I find almost unbearably beautiful. The very same species that looks so small in that photograph is the species that took the photograph. We are the dust mote that learned to build machines and fling them to the edge of the solar system and turn them around to see ourselves from the outside. We are small, yes, but we are the small thing that looks up and wonders and goes. There is something magnificent in that. The cosmos is vast and cold and indifferent. And into that vastness, a tiny, warm, curious creature reached out a hand and said, "I want to know." That's why we go. Not for profit, not for power, not even, in the end, for survival. We go because the alternative, to sit on our little dot and never look up, never reach out, never wonder what's beyond the edge, would be a kind of death of the spirit. The Voyagers are the physical embodiment of our refusal to stop wondering. They are curiosity made of metal and circuitry, our questions given form and sent out into the night to find answers. And whether or not the golden record is ever found, whether or not we ever meet anyone else out there, the act of reaching is its own justification. We went because we are the kind of creature that goes. And that, I think, is something to be proud of. So let's come back one final time to where we started. 2 small spacecraft launched in 1977 that were only supposed to photograph some planets. And look at everything they became. Look at everything they taught us. They showed us that the edge of the solar system isn't Pluto, isn't a planet at all, but an invisible wall of magnetism and plasma, a boundary where our sun's reach finally gives way to the wider galaxy. They crossed that wall, the first things ever built by human hands to do so, and they found a boundary far stranger than we'd predicted. Sharp where we expected gradual, hot where we expected cold, magnetically aligned where we expected chaos, pressed in by a galaxy denser and more forceful than our models had assumed. Almost everything we thought we knew about the edge turned out to need revising, and the revisions came from real measurements, from actual contact with the region we'd only ever theorized about. They revealed that we live inside a shield, a vast protective bubble that knocks down a huge fraction of the galaxy's deadly radiation before it can ever reach us. A defense system most people never even knew existed. They taught us that this shield is not permanent, that it breathes with the sun's moods and shrinks and swells as our star carries us through the changing neighborhoods of the galaxy. They gave us the data we'll need to protect the explorers we send out next, the astronauts who will one day walk on Mars, carrying with them models built in part from numbers, a 1970s spacecraft gathered at the edge of everything. And they raised 100 new questions about the shape of our bubble, the behavior of magnetic fields, the hidden worlds that might still lurk in the outer dark, questions that will drive the next generations of explorers forward. And beyond all the science, they did something else. They carried our story outward. Bolted to their sides, 2 golden records drift through interstellar space even now, carrying the sound of a heartbeat, a greeting in dozens of voices, music and laughter, and the image of a world. Long after we are gone, long after the earth itself is gone, those records will still be out there, the last enduring whisper of a curious species that once looked up and decided to go. The Voyagers will outlive us all, sailing through the galaxy for billions of years, our messengers to a future we cannot imagine and will never see. The next time you step outside on a clear night and look up at the stars, I want you to remember something. Out there, in a direction you could point to, further than your mind can truly grasp, Two small machines from the 1970s are still flying, still drifting outward through the space between the stars. Still, even now, their power nearly spent, whispering faintly back to the planet that made them, telling us about a place no one had ever been. They crossed the edge of the solar system, and they found that the edge was only the beginning, that beyond it lay a galaxy vaster and stranger and more wonderful than we ever imagined. And beyond that galaxy, more still, an endless cosmos of mysteries waiting for someone brave enough and curious enough to keep going. That's what's out there. Not an ending, a beginning. The edge of the solar system isn't a wall that shuts us in. It's a doorway that opens out onto everything. And we've only just taken our first step through it. Thank you for coming on this journey with me. The Voyagers are still out there, still teaching us, still reminding us of who we are and what we're capable of when we dare to look beyond the edge. And the next time you wonder whether any of this matters, whether the reaching and the wondering and the going are worth it, just remember those two tiny spacecraft, further from home than anything has ever been, carrying our story into eternity. We were here, we wondered, and we went.